So at the end of the last clip, I was just going over this, that um, when the ratio is -1 to +1, this gives us our working range of our buffer. And to take the inverse log, to write this without the log term, we raise both sides. We raise 10 to the power of both sides. So 10 to the -1 is equal to 10 raised to the power of log 10 HA over A, and 10 raised to the power of log 10 cancels that log term. So 10 to the -1 equals this ratio, 10 to the 0 equals this ratio, and 10 to the 1 equals this ratio. And if we solve these terms, 10 to the 1 is 10, 10 to the -1 is 0.1, 10 to the 0 by now we all know is 1. And that gives us the ratio is equal to this value. And if we use that simplifying term that sorry, get my pen going, that HA plus A equals 1, then we can take these expressions and substitute them in for the A value here, and then solve that. So again, this simplifying assumption here only works in the case of two solutions of identical concentration with regard to the conjugate base. It doesn't work for the situations where you have a weak acid with a small amount of strong base, or a weak base with a small amount of strong acid, or if you're using an amphoteric substance. So if we can't use the simplifying assumption that we use in our pre-lab calculations, then how do we do it for a weak acid plus a small amount of strong base, or a weak base plus a small amount of strong acid? Well, that's where we use the ICE table. That's where the change that's made by adding that small amount of strong acid or strong base is this is how we keep track of it. So again, remember that you must have a balanced chemical reaction. Otherwise, you can't calculate the change. You need to know what the mole ratio is. Now, for the example we're using, the mole ratio is 1. So forgetting your reaction, the situation is forgiving, because if you forget the reaction, you tend to assume it's 1. But there are cases where it's not 1. So if we had calcium hydroxide, OH2, now we have 2 hydroxide ions for every mole of calcium hydroxide. So if you don't have a balanced equation and you have this kind of situation, it's going to be it's going to be a problem. So I'm going to go through the steps to completing an ICE table or RICE table, and then I'm going to go through an example that doesn't come from the information that I provided you so far, just so that you have an independent example of how to do it. So the steps to completing an ICE table are: balance the chemical equation. So very important. You fill in the amounts that you were given in the statement of the problem. And then you fill in the amount of change for each compound. And I'm going to show you how to do that. And then you're going to solve for the equilibrium amounts. And I'm going to show you how to do that. So here's the example that I'm giving you. What is the concentration of the hydronium ion? Or we could say, what's the proton concentration? Remember, square brackets denote concentration. And what is the pH of a 0.534 molar solution of formic acid? And I'm giving you some information. I'm telling you it's formic acid. This is the acid that ants produce. When an ant bites you, it's injecting formic acid, and that's the irritant that causes an ant bite to itch. The chemical formula for formic acid is HCOOH. And here is the condensed structural formula for formic acid. The Ka for formic acid is 1.8 times 10 to the minus 4. And if I take the negative log of that number, I get 3.73. That's the pKa for formic acid. And note that there are two significant figures in the Ka, and there are two significant figures in the mantissa of the logarithm. Note the characteristic doesn't count towards the significant figures. So the general dissociation reaction, acid plus water gives us conjugate base, or the anion, plus the hydronium ion. I could also write that out as HA gives me A minus. And then I don't have the water term and the hydronium ion term to balance. My balanced chemical equation for the ionization of formic acid, all of my coefficients are 1. It's balanced as written. And then just to reinforce some information that we've covered earlier in the semester, here's the condensed structural formula for formic acid. We protonate the water molecule. We have this bent water molecule. Sorry, here's the bent water molecule. It has the extra proton on it. Here's the lone pair. It's it has 4 electron domains, so it has a tetrahedral electron domain geometry, but it's trigonal pyramidal because there are just the 3 protons there. Anyway, so this is our given information. If we write our ICE table, good idea to write the balanced chemical equation up here at the top of the ICE or RICE table. We're given our initial concentration, 0.534 molar. The concentration of water we weren't given, but we know it's huge. It's by far most of the molecules in solution are water. At the time 0 situation, the concentration of ionized formic acid is 0, and the concentration of protons or hydronium ions is essentially 0. I have this essentially, or the tilde indicating essentially equal to 0, because there's still the Kw of water, which is why I didn't write actually 0. But mathematically, we're going to treat it as 0. So now, what is the change? Well, we don't know. We put 0.534 moles of formic acid in water, and some amount of formic acid ionizes. Just some amount. I don't know what that amount is. So I'm going to say that amount is X. I'm going to use X as a placeholder for some unknown amount. And I give it a minus sign because the amount that ionizes decreases the concentration of formic acid. So just some amount disappears from this side. And for my balanced equation, whatever that amount is, that some amount, that X, that very same exact amount appears as formate. That's what my balanced chemical equation tells me. So it's also X, but the sign is plus because it's increased. And then the number of protons that have been produced, or the number of protonated water molecules, is also that same exact amount, X, and the sign is positive. So that's my change. So while it might seem intimidating, it's actually pretty easy. There's just some amount, and I'm going to call it X. Now, What is my equilibrium concentration? Well, if I have 0.534 molar to begin, and I lose some amount that I'm calling X, the new concentration is just 0.534 minus X. The amount of water is still very large. It's huge in comparison to all these other numbers. So that's not changing. And then the amount of formate, or the conjugate base that's formed, is X, and the amount of protons or hydronium ions that's formed is also X. So that's my equilibrium concentration. Now I want to solve this. So how do I do that? Well, I go to my acid dissociation expression, and we know that Ka is 1.8 times 10 to the minus 4. We were given that back on this slide. Ka is equal to 1.8 times 10 to the minus 4. And then I know from my balanced chemical equation that I have products over reactant, not including the solvent, not including this very large number. So this is my mathematical expression. So now I just want to take these values of my unknowns in my acid dissociation expression, and I just want to plug them in and rewrite that expression. So Ka is 1.8 times 10 to the minus 4, and then I have hydronium ion concentration and formate ion concentration. Those are both X, so it's going to be X times X, and then the denominator is going to be 0.534 molar minus X. So I apologize here. When I made the slide, I transcribed my numbers. So this is 0.534, not 543. So I have X squared over 0.534 minus X. A very small simplification is just to write X squared over 0.534 minus X. So that's how far I've gotten so far. Now, if I go to the next step, I can make a simplifying assumption. The amount, and I began earlier in the slide saying that when I have a Ka, the concentration of the unionized acid is generally much, much larger than the ionized form. So the number X is a small number, and the number 0.534 is a big number. So a big number minus a small number is still a big number. If the difference in subtracting X is small, if it's less than 5%, then I can make an approximation to say that that number is basically unchanged. It's the same number within 5%. So that's the simplifying assumption I'm going to make. The relatively large initial concentration and the small equilibrium constant allows me to use this simplifying assumption that X will be much less than 0.534. So if I do that, then I just ignore this minus X term, and I can rewrite this as 1.8 times 10 to the minus 4 equals X squared over 0.534. So now that's a much easier equation to solve. I can solve this equation. We don't do it in Chem 100, but I can solve this using the quadratic equation. So if you're comfortable with mathematics, I can show you. Maybe I'll post that as an extra video solving this with the quadratic. If you go on in chemistry to take Chem 200, you would be I'm not even sure if you do it in Chem 200, but this can be solved analytically to an exact answer. But these approximations are very, very good. So that's really all you need to do. So if I have this simplified expression where I just have 0.534, I've